Thank you for the introduction. Good afternoon, everyone, and welcome back from the lunch. My name is Thitiporn Kaewpetch. I'm from Kasetsart University, Bangkok, Thailand. Today, I would like to talk about the influence of particle arrangement in coating layer on barrier properties for bio-based plastic. First of all, bio-based plastic is made from the natural resources, right? And it is either non-biodegradable or biodegradable. And because of the environmental issues, so of the biodegradable packaging is growing globally. And it has been predicted that the demand for the biodegradable packaging will be increased around 17.4% from 2018 to 2026. And most of the products for the biodegradable material that has been focused on are the plastic and paper. And most of the industries that adopt these biodegradable materials are the food and beverage industry, healthcare industry, home care industry, and personal care industry. But even though we use plastic, biodegradable plastic, but and some of the biodegradable plastic have the properties very similar to the properties of the polyolefins, especially the mechanical properties. But the limitation of the biodegradable plastic is the barrier properties. As you can see in this graph here, the biodegradable plastic, which is shown in the green color here, has the higher oxygen permeability and also water permeability than the petroleum-based plastic, which is shown in the red color here. So you can see that and how we can improve these barrier properties. So the approaches to improve the barrier properties of biodegradable materials includes, there are two approaches. The first one is shown in the top part here, which is about the modification of the plastic matrix. You can either make develop the chain architecture. For example, you can make the polystructure more crystalline, so the structure is denser and closer, so it can retain the gas molecule to penetrate. Or you can incorporate the fillers into the particle matrix in order to increase the tortuous path of the gas molecule to travel. Or you can make the polymer blends more miscible or more compatible. So in this case, you can improve both mechanical properties and also barrier properties. Another main approach we can use to improve the barrier properties of the packaging is to make or to create the multi-layer structure, which is shown in the bottom part here. So to create the multi-layer structure, you can either use the co-extrusion or creating the a thin layer or a layer of the coating on the surface of the substrate. Okay, for the coatings, we have different techniques or different methods. We can use the vapor deposition, or in this vapor deposition, it can be either chemical vapor deposition or physical vapor deposition. But in this case, it requires the high energy and also the vacuum conditions. But for method is a layer by layer assembly, which it is the method to create layers with different or opposite charge on the surface. And another method for the coatings is the electrohydrodynamic process, which include the electrospinning or electrospinning, and also the most about the coatings. In this solution coating, which we're going to focus on here today, is include the bar coating, spin coating, solid coating, and dip coatings. In terms of the gas permeation of the gas molecules, basically when the gas molecule tries to penetrate or permeate through the membrane of the plastic, it has 4 steps. So the first step is the gas molecule absorb on the surface of the membrane or the surface of the plastic, and then the molecule will dissolve in the matrix of the membrane, and then diffuse the membrane and dissolve from the layer, the surface of another side of the membrane. And this diffusion of the gas molecule is driven by the concentration gradient. So it means that the gas molecule would travel from the the side or the area that has a high concentration to the low concentration. Okay, and so from this, it means that the permeability of the gas molecules is the product of the diffusivity and the solubility of the gas molecule. And diffusivity and the solubility is proportional to the free volumes of the matrix. And this free volume, it means that, as you can see in this equations, you can see that if the free volume of the matrix increases, it will increase the diffusivity and also the solubility. So when this diffusivity and the solubility increases, it will increase the permeability of the gas molecule. So there are some studies that try to minimize the free volume of the coatings or the films by making the structure is more alike. So in this case, they use the CNC, which is the cellulose nanocrystal, which has the rod-like structure the film shear force to or the structure. And you can see here when they use force, you can see that from the random packing of the structure of the coating layers, when you use higher shear force, you can see an more ordered structure of the coating layers. From this, they can see that when they use the higher shear force, or when they have the more allied of structure of the particles of the CNC, you can see that the oxygen permeability and also the carbon dioxide permeability decreases. So, and this case is about the rod-like shape, but what about the spherical particles? So in spherical particles, if we want to make it another structure, we can use either atomic layer deposition or ALD. So in ALD is a subset of the chemical vapor deposition, in which, as I mentioned before, that is require high energy and also need the vacuum conditions. In this technique, it has the surface limited reactions, and the benefit is it has pinhole free. Okay, but another this is about the solution-based coating. As we have the deposition. In this case, the particle will be deposited on, will be floating in between the on the air-liquid interface and form a monolayer in here. And this monolayer of the particles will be transferred into the substrate when the substrate is moving. Okay, but if you want to make the multi-layer structure from this method or this technique, you have to do multiple things. But if you want or monolayer, you can use the convective deposition. So for the convection, basically, this technique will involve the evaporation of solvent and the capillary force between two particles. In the system of this convective deposition, it will include the deposition blade, which is like here, and the substrate, which is right here. And there is an angle between the deposition blade and also the substrate. And when you want to deposit the particles, you have to inject the particle suspension over here, and you have to put the substrate right here. And when you move the substrate, the substrate will drag a thin layer of the suspension. And in this area will be an evaporation of the solvent. When there is an evaporation of the solvent, right in this area, there is the mass balance so they try to drag this suspension in the bulk to this area, and it will bring all the particles to this area as well. But how it formed the order structure? It formed the monostructure, order structure is because of the capillary force. So when the two particles are close or stay close together, close to each other, distance between two particles, and it induces the capillary force, which two particles together and form a order structure. And this movie is showing the forming of the order structure of the silica particles. This is the movie from the confocal laser scanning microscopy. Okay. And from this method, you can get the multi-layer or layer as well. And from this method, from the convective deposition, you can have final structure is the closed packing structure, which is FCC or HCP, which has the atomic packing factor around 74%. So from this, we just wonder if we can make the compare between the random packing structure and the order structure, how it influences the barrier properties. So from our experimental setup, we use the 1 micron size and 200 nanometers of the silica particles. We try to investigate the 1 micron size first because is the optimum size that can easily make the order structure from the convective deposition technique. And for the substrate, we use the polylactic acid or PLA film, which has a thickness of 17 micrometers. And before we start the coatings, we have to pre-treat the surface by using the oxygen plasma treatment. It's because when we have to do a pre-treatment of the surface because for making the order structure, really need to have a very hydrophilic surface to make it. So after we pre-treat the surface, we use the convective coating technique to make the order structure of the coating layers. And then we will use the blade coating to make a random structure. And then we will characterize all the surface properties of the coating layer film, and then measure the barrier properties. Okay. So this is the film appearance and diffraction of the 1 micron size silica particles coating. From this technique, we will get the three structure. The first one is the random structure is right here, and you get the order structure and also submonolayer from the convective deposition technique. As you can see here, from the random structure, we will get from the blade coatings, and for the order structure and submonolayer, which I mentioned, that is generated from the convective deposition technique. In this technique, if we increase the speed, coating speed, it will also change the structure of the coating layer. It will change from the order structure to the submonolayer. Okay, and if you look at the visible light diffraction of each structure of the coating layer, you can see that for the random structure, you cannot see any structural color of the film at all. But when you look at the order structure, you can see some structure, a very clear structural color and or iridescence of the film. This is due to the diffraction from the neighboring planar from the latex, crystal latex. Okay, and also for the monolayer, you can also see some area that shows the structural colors or the iridescence. But there are some areas that doesn't show it very clearly. This is because of some defects on the surface. Okay. And when we look at the laser diffraction of the coating layers, you can see that if we have the order structure, you can see a very clear single dot surrounding a center point here, which show that this structure has six neighbor particles surrounding one center particles. So this is showing that the structure of the coating layers is the SCP, or hexagonal close packed structure. Okay, but for the if you random structure, the single dot, but you see the cloudy of the diffraction. Okay. For these confirm with the structure with the scanning electron microscopy, or SEM. So we can see a very clear structure, a very ordered structure of the coating layers of the silica particles, and you can see that we have. If you look at a single dot here, you can see six neighbors particles surrounding one center particles, and this is the hexagonal close packed structure. But for the subnodal layer, you can see that some area doesn't cover with the particles. Okay. But when we look at the when we use this technique, when we increase the coating speed, the thickness of the layers also changes. So it will decrease the thickness of the coating layers. And the maximum thickness for the other structure that we can get is around 3 microns. If we have more than 3 microns, it will form some cracks. Come back here, as you can see that we have subnodal layers, or even though we have order structure and the subnodal layer, but how can we know that how close the structures are, or how, in this case, how the coverage area is, how much it is. So we can use another technique to check this coverage area and the density of the particle, the density of the structure. So we can use the confocal laser scanning microscopy to investigate or to visualize the coating layers. Actually, the confocal laser scanning microscopy, it can visualize 2D scan and also 3D scan. So this is the picture of the 2D scan. And from this 2D scan, we can use the 2D particle tracking, which is developed by the John Kruger and Eric Weeks. And from the 2D tracking here, we will get the position of each particle. And we can use this position to calculate or estimate from the algorithm, get the coverage area and also the density of the structure. So for the density of the structure, we can use the Voronoi area, which is about the area of center space that is closer to this order center. So if the structure has more has the HCP structure or hexagonal close packed structure, it will have the Voronoi area is around 0.866 micrometer square, and structure, the coverage area is pretty much higher, is above 80%. But for the subnodal layer, this coverage area decreasing lower than 60%. And for the Voronoi area, which is showing the density of the structure, showing how close the structure is. So it's showing that the other structure has a very sharp peak at the normalized Voronoi area equals to 1, which showing that this order is very close and is very similar to the structure of the HCP. When you look at the random structure here, you can see that the distribution of the Voronoi area is broader, and the peak of the distribution is shifted higher normalized Voronoi area. So it's showing that this Voronoi this structure is broader and is looser than the other structure. And for the structure that has the submonal layers, you can see a very broad distribution. So the structure is even broader and looser. So from this order structure of the coating layers, from the random to the order or submonal layer, you can see that when we have the random structure here, the order structure of the coating layers, we have the water and also the oxygen permeability lower than the random structure. And also it will even lower. It's even lower than the when we have a smaller size of the particles here. But we still looking forward to the more explanations about this technique. Okay, so to summarize all the talk today, so the properties of this order packing structure is slightly better than the random structure, but the free volume is still exit in this coating layers. So some binders or some binary suspension system could potentially used to study to improve the barrier properties here. So finally, I would like to acknowledge and thanks the first the Department of Material Packaging and Material Technology, and also the Kasetsart Research Institute for funding the project and also supporting our travel. And also we have to thanks to the nanotechnology, which is the national institution, national lab in Thailand, for providing the resources as well. So, and thank you for your attention. Thank you very much.